Hello and welcome. I'm Mark Ernst, heading the Applied Cognitive Psychology group at Ulm University, and I want to tell you in this little video a couple of studies that we have done recently together with Charlotte Roy, a postdoc in my lab within the framework of the CrowdDNA project. The CrowdDNA project in general is interested in how we manage a crowd, how we interact within the crowd, and that from the very small scale, the microscopic scale, to the macroscopic scale of huge people of crowds. Our task is more on the microscopic scale, looking at individual people and how they are behaving within the crowd and how they are behaving in general. So what I want to tell you here is about a couple of projects that we have done recently on spatial orientation and on locomotion, which are very important tasks when you are within a crowd and you want to find a way out, if you want to find a way around within the crowd. So you have to know where you are in this space, and when you locomote, you have to know where, for example, finding the goal. And this line of research started already quite some time ago with probably the most simple task I've ever done, which is asking people to walk as straight as possible for a longer period of time. In this case, it was up to 4 hours. And it was inspired actually by a TV show that asked us whether it's true that people, if they are lost in the desert, that they have a hard time to find their way out because they start running in circles. And since there wasn't too much literature or research done in this topic, we did studies around that, and the task was, well, to walk as straight as possible, find your target within a 4-kilometer distance or something like that, and then we recorded their navigation performance. So the idea, of course, for a desert is that there are no landmarks. So basically, you can simulate a desert environment very easily by just blindfolding people and see how they then navigate if they don't have any visual information possible. We did this by blindfolding people. We put a sack on their head and then we asked them to walk straight. We did this in an environment on a Dutch little island called Vlieland, together with Jan Sorman back in 2009. And the task was, as I said, as simple as it can be. And the surprising thing is that we wouldn't need any big environment for doing that study, because people very quickly start running in circles. Basically from the beginning here, the green dot is where people started, and with immediately they started running in circles, or in spirals, better to say. The circles got bigger and smaller, and maybe also at the end there was a stretch where they got more and more straight, and sometimes they even walked in the opposite direction. So you can see here on this scale that the circles are as small as 15 meters in diameter, so they would easily fit within a room. And that's when you have no visibility available. And that's, of course, if you try to walk straight and you walk in circles immediately when you don't see anything, that's pretty much similar that in a crowd, for example, if you don't see any distant landmarks, you only have people around you and try to navigate, find the exit or something like that, you'll probably have a hard time doing this if you don't have landmarks available. And you only trust your thing, particularly in the environment. Maybe it's quite dark often, and there are many people around you. Okay, so why is that? Well, if you ask people, the most prevailing hypothesis was, and still is nowadays, that there is some asymmetry in the body, that either one leg is stronger, one leg is longer, and that may be the reason for why they are running in a circle. But that can't be true, because, very simply, as I already mentioned here, sometimes people actually, when they start walking to the left, they turn and start walking to the right within one go. And certainly their leg doesn't change that quickly. So we recorded many people and looked at that already still back in 2009. And we found like KS here, he was really turning always to the left. But as you can see, the people below, sometimes they're going to the left, sometimes they're going to the right within one go. And if you look at the statistics of all that, people are pretty much going straight. Some of them, like KS, as you can see, has a direction bias to the left, and someone like SM at the very bottom has a bias to the right. But overall, yes, people are sometimes going left, sometimes going right, but overall, this is a nice, looks almost like a normal distribution, a cumulative normal distribution, or centered on zero, meaning they are going straight on average. So why is that? Well, if you don't have any visual cues available or any external cues from audition as well, you have to trust on your inner sense. And the inner sense is the vestibular organ that tells us where straight ahead is. And that vestibular organ, like any other organ, is noisy. But it only senses acceleration. In order to get a direction estimate from the acceleration, you have to integrate a signal. And we know very well if you integrate a noisy signal, you get a drifting bias, which is called a random walk. And that's what we believe what is happening and why people are not going in straight but in circles. If you have your direction estimate and this is offset slightly, and that makes a random walk, that means it walks slightly to the left and slightly to the right. And if you put in physiological parameters, you can see that that makes paths like that. That's now simulated with a step length of 75 centimeters. And that each step there is a random number added to the previous one on the direction estimate, like shown here. And that sometimes makes you that over some stretches of this, from here, minute 10 on, you're pretty much going to the left. In the beginning, you were going to the right. Okay, so it's noise accumulated in the vestibular system that makes us going in circles. That's what we believed at that time, and we wanted to see with Charlotte and within the CrowdDNA project whether that's actually true, that it's a random thing. So we had people run for a longer period of time than only these 50 minutes as is displayed here. And we've repeatedly measured them over several trials, 10-minute stretches, and then also over several days. And that's what this looks like. This is one particular participant. Here you can see him turning on trial 1, on trial 2, trial 3, trial 4, and trial 5. And this particular participant is, yes, going always in the same direction on day 1, as is displayed here. But now if we look at the same person on day 2, well, on day 2 we pretty much make some random things going to the left and then going to the right, more or less straight, and then on day 3, sometimes to the left and sometimes to the right. So the prediction of these data would be, if I plot the 3 days and the 5 trials across the 3 days, if I plot the mean angular velocity against the days and the measurement, then you will see, well, if they're going always, if they're perfectly straight, all these dots would be on 0. If they are starting with turning to the left and then to the right, it would look like this, it would go down. And if they have a constant bias to either the left or to the right, it would be different from 0 up here or down below 0. If we look at the data, pretty much the people are at random, and if I look at the average across the 3 days, there's almost none that is significantly different from 0. There are 1 or 2 within the 3 days, but I'm sure if we measure them longer, they would also return and go to the opposite direction at some point. So it seems really to be a random process, and confirms the hypothesis that it's due to the vestibular system, which is noisy, and that disorients us. If we don't have any landmarks or so available that helps us to calibrate our vestibular system, it gets this drift, and which will disorient it. And blind people know that quite well, that this can happen, and they suffer from this problem as well of disorientation when there are no distant landmark cues, in this case from audition or any tactile or whatever other cues available that would tell them a direction estimate. Well, now, of course, in a crowd, it's probably not that you have no vision, but sometimes you have a little bit of vision. And we know that these stories are also true, that people get lost in a desert, not only in a desert, but also in the jungle. And so we try to repeat these experiments in a jungle-like environment. So we found a German forest close to Tübingen, where these studies were done originally, in Karlsruhe, the Bienenwald, which is nice and flat. The trees are not too dense, so you can easily walk. There's not too much underwood. But the task was exactly the same. We indicated a direction, and the person had to walk straight as good as possible for a stretch of 3-4 hours. And what we can see here is that people also walk in circles. Days were cloudy days. There was KS again. Now this time there was the same person as before, always going to the right. Now he's always going to the left. So in the opposite direction, a couple of days or weeks later. And we have multiple people like that. They always walk in circles, sometimes to the left. The circles, as you can see here, there's the scale of a kilometer down there, are bigger than this 15 meters than we had before. So they are in the order of 200 meters, which makes sense. If you have vision available, you integrate it. You're not walking as tightly in a curve as when there's no vision available. So yes, the visibility helps, but it's still disorienting you. But then we also had people that walked on a sunny day, and the sun is like a landmark, and then people are walking much more straight. There was one person, MJ, who even left the forest, so we had to turn him around and send him back into the forest. The interesting thing is, of course, if the sun gives you a direction estimate, you would predict that if that's the only cue they have available for navigation, you would walk in the direction of the sun. But people are actually walking more straight than, because within 4 hours, of course, the sun is moving quite a lot. That's indicated by these arrows. We wanted to do these studies, and we have done a couple of these studies also in the lab. And for this, we needed a treadmill. And at that time, back at the Max Planck Institute in Tübingen, where I was at that time, we built a so-called omnidirectional treadmill. That was a treadmill that you can walk independently in all directions. And there was Martin Schweiger, predominantly from the TU Munich, who built that within another European project called Cyberwalk. And it was constructed of 25 belts which go in one direction. They are mounted on a chain, so the chain motion could go in the opposite direction. So you have X and Y, and put together you can walk in any kind of direction. Here's a little video that would indicate that we have taken at that time together with Jan Sommen. There were a couple of other partners involved in this project, indicated on the right. You will see in a second a little how you actually can navigate here in all directions. Step up, down, step to the left, step to the right. This machinery was quite big, so unfortunately I couldn't take it along and couldn't maintain it for that, so it's not available anymore for studies. But it was a very useful tool to do navigation studies and locomotion studies in confined lab spaces. Okay, now we have seen in the last couple of times that landmarks matter for navigation, and that's not new. But still, we pretty much don't really know what a landmark is and how a landmark can help us. Because most people assume a landmark to be some static, iconic feature somewhere where it's in the far distance that can help you to go to that target. But it makes sense that also probably less persistent, less salient cues can be used as a landmark environment. And we've studied that, as you can see here, in this 360-degree a projection screen that we've developed with a colleague in Bielefeld, Professor Boch, and we've looked at how the persistency of a landmark helps us to navigate. So the question was, what makes a good landmark? As I said, yeah, this church in the back that's there already for a couple of 100 years, that's what everyone thinks of as a good landmark. But maybe that bicycle in the front, which is nice and red and also quite distinct, that may also be a good landmark. The problem is that it's probably not there anymore when you leave, so it's not persistent. It has a temporal characteristics. And the question that we had is, do these temporal characteristics matter, and do people still use something like this bicycle as a landmark for navigation? Do they take that into account? So as I mentioned, we took that into the lab, this kind of question, and we made an environment consisting of 3 landmarks, whereas 2 of them were persistent, they were always there, and 1 that could jump around. The task was to find the target, which is this bucket in the middle of the 3 landmarks, and in a training phase, then this non-persistent landmark was jumping around from trial to trial, and was moved in the back of the person after they've picked up that target bucket. And what we did then is, in order to test whether that landmark played any role for them still, is for them not knowing, we moved the landmark from 10 meters all the way to 16 meters from trial to trial. And then we asked people, or we looked at how people, where do they navigate? So where do they think the target has been before? And if this landmark, this non-persistent landmark, has any weight, they would now move further towards that landmark. And by looking at how much they move towards that landmark, we can see how much weight is given to them. And the prediction would be, if you have a persistent landmark, you should give it a high weight, so you follow it more than when it's a non-persistent. In a non-persistent landmark, you should give it very little weight, and you basically should be able to find better to where the actual target position was, because you don't really use that non-persistent landmark. Okay, and here is what we find, the accuracy. So how are you? And the permanent training, as you can see, they're deviating from 0, 0 would mean the position of the target location. Now they are moving towards the non-persistent landmark in the permanent trial. In the non-permanent trial, they are much more staying towards 0. So as predicted, the weight given to non-permanent landmark is much less than it is to the permanent landmark. As it should be, the persistency should be taken into account, and you should weight it based on how non-permanent it is or how permanent it is. This is one person. Of course, we've measured many more people, and on average the same pattern results. So there's a weight given to the permanent landmark that's higher, it's closer to 1 than to the non-permanent landmark. So we take these landmarks into account, but we've done all of these basically pretty much on flat ground. The navigation was on the 2D treadmill or in the flat ground, but the environments that we typically navigate are pretty much the steps, stairs, they're walking up, down, and so on. And of course that also will have an effect on how we perceive the 3D world. So we recently built a virtual environment that allows us to study navigation on 3D spaces. And that treadmill here is consistent, or is sitting on a hexapod motion platform, has some visualization. Of course, you always need some tracking in order to know where the person is. This is what that looks like in action. That was built together with Dennis Wiebusch here at Ulm University in the last couple of years. The hexapod has quite a working range, or can go pretty much 30 degrees in all directions, has 6 degrees of freedom, and you can freely walk on it. In this case it's unidirectional that you can walk, but you can walk up and down. as you can see in a second in this little video here. And with this, we asked the question, how does the third dimension play a role for you orienting space and you finding back home? So is there any difference between the two-dimensional space and the three-dimensional space? And that study was a little bit inspired by some studies that had also been done in Ulm quite some time ago on the desert ant. The desert ant is known that it uses path integration, so to integrate the path, but it also is known that it takes quite some distances out and then has to find back the nest. And for the desert ant, a little rock is a 3D environment which is massive. So my colleagues have done that more thoroughly or more systematic. So they built these little bridges here where you can walk up and down as a desert ant, and then you walk up and down this checkered path, and then you have to find back to the home position on the straight path. And the prediction would be, of course, if you're not taking any other cues, only proprioception and path integration into account, because the path going out over this bridges is much longer, you would much overshoot when you have to find back to your nest. So we have built a similar thing for humans where you walk up and down the bridge, and the task was pretty simple. People in one go had to go out and then either find back home both on the flat, or they had to go out over the bridge and then find back home to the starting position. And the prediction is, since the path over the bridge is much longer, if they only use path integration, they would now overshoot. This is the over and undershoot. On the flat, people are pretty much finding home correctly. In the 3D task, the prediction would be if they find, then they take the 3D environment into account, they would go home correctly. If they do path integration, PI, the prediction would be they are overshooting. What we actually find is that they are largely undershooting, which was quite surprising to us at the beginning. However, if you look and do this task, once you realize this bridge is not very steep, but when you're walking it, particularly blindfolding, you think this is much steeper than it actually is. And there is quite some literature on this, on the misperception of slopes, that has been done in many different things, verbally reporting or proprioceptively reporting and so on. And typically people find, like when you can see here, if you have a physical slope of 10 degrees, that's almost perceived as 20 degrees. Not quite, but almost. So there is quite an overshoot, which is massive of that. And if that's the case, if you're walking over here, and you have to find back home, but you perceive an environment like that, of course you're massively undershooting, and that's the prediction for this. And the interesting thing is we changed the mode of locomotion. We asked people to crawl, we asked people to, we made the slopes into steps, so you have to walk up the stairs. And the interesting thing is if you walk upstairs, so there's really not a sloped environment, then people are pretty much correct in finding home, so there's no effect. While when they are crawling and you still have to crawl up a slope, then you have the same kind of effect as if you're walking, pretty much. So whenever you are on a sloped surface, you're massively overestimating how steep that is, and that affects also your navigation behavior. And that's why it's important when you don't really see anything, because you're maybe in a crowd, because you're maybe in an environment like a firefighter that has no good visibility, then you have to trust your inner senses from proprioception, from your vestibular system, and this can massively bias the way you perceive the environment. And that's why it is also important here for this CrowdDNA project. Okay, with this was a short outline of a couple of studies that we have done in the last couple of months and years. And with this, thank you for listening.